Hello, welcome to Basics of Finite Element Analysis Part 2. Today is the fourth lecture of the current week. Yesterday we were discussing the plane elasticity problem and we had described all the details of the same problem. There was one thing yesterday when we were discussing that I had described this constant as C12. So, this was a typographical error, and instead of C12 it should have been written as C22. So, this is the correct term. So, these are so what we have discussed till so far is the governing equation of motion, stress strain relations, strain displacement relations, and then the definitions for C's, the C matrix C11, C22, C12 for plane stress and plane stress problems, both for orthotropic and isotropic materials. There was one more thing which we should discuss before we start discussing the finite element formulation, and that is tractions. So, what is traction? So, traction is there is any force, any stress which is being applied on the boundary of the body, it will have an x component and it will have a y component. So, these components are called tractions. So, Tx is, so this discussion is happening in context of boundary conditions. So, Tx is equal to sigma x times nx. So, at any point, suppose there is a, this is a surface and I am applying some sigma x here, okay. So, at this point or in this, suppose over this zone I am applying sigma x and I am also applying sigma y and I am also applying shear stress. I can apply all three of those. Then, and if I know these conditions, so I am applying some forces in this direction, then sigma x times nx plus sigma xy times ny is called traction in the x direction. And if it is specified, I will say that its value is Tx hat. Okay. So, if I know sigma x, sigma xy, sigma y or whatever, then I multiply sigma x by nx, sigma xy by ny, I get sigma x, this Tx hat. Similarly, Ty equals sigma x y nx plus sigma y ny, and if I have know its value on a surface, then I say that its value is Ty hat. So, let us say these values are known on some portion of the boundary, let us call that portion of the boundary gamma 2, let us say this is gamma 2, this is the boundary. So, the overall boundary could be like this, entire boundary is gamma, a portion of that boundary on which tractions are known, I call that gamma 2, right. Similarly, so these are secondary boundary conditions. What kind of forces I am applying on an external boundary? I have to know those. If I am applying those forces, I have to know those, otherwise I cannot solve for the problem. And the other thing is there could be some other portion of the boundary, let us say this one. So, here tractions are known, here displacements could be known. So, let us call this boundary as gamma 1, and on this boundary u is equal to u hat and v is equal to v hat on gamma 1. So, these are primary variables and these are secondary variables. Okay. So, we know that. So, the hat indicates it is already known and specified. So, this is what the boundary conditions are. So, now we will start developing a finite element solution for this problem. And what is the process? What is the first step when we start doing finite element solutions? We discretize the domain. Second step is we develop a weak form. So, we develop a weighted residual statement and then from that a weak form of the statement. Once we have the weak form of the statement, then what do? We have already discretized the domain. For each domain we have developed a weak form. Then we introduce approximation functions. So, in the first step, domain has been broken into smaller parts. In the second step, we have put weak form. In the third step, so first step we broke the domain or we approximated the domain, right. When we discretize it, we are approximating it. Then in the third step, we are approximating the function for primary variables. So, this is first approximation, this is second approximation. So, once we do this approximation for primary variables, we get, what do we get? We get FE equations, finite element equations. For each element we get a set of equations. Then what do we do? Assembly. Then we apply boundary conditions. Now, in this case, is it just boundary conditions? So, here I am also including time effects, right. So, if it is a dynamic problem, I have to apply boundary conditions as well as initial conditions. The sixth step is we solve, and seventh is we post process the data to compute whatever entities we are interested in, strains, stresses, whatever, moments. So, this is the overall roadmap, and this roadmap has been consistently throughout this as well as the previous course. This has not changed, and in any finite element analysis problem, this is the roadmap. You discretize, you develop a weak form. Well, in some cases you may not develop a weak form, but you will have to do with the strong form, but somehow you develop. Then you apply approximation functions for primary variables, you get finite element equations, you assemble them, apply boundary conditions and initial conditions, solve it, and for post processing you do post processing operations. So, now we will start doing that. We will start with our development of weak form. Okay. So, we will write down the equations. Now, as we write down these equations, for purposes of brevity, I will write del u of partial derivative of u with respect to x as ux, partial of u with y is uy, partial of v of x as vx, and partial of v of y as vy. So, my equations of motion, so let us call this equation A, these are equations B, and these are equations C. What we want to do is, we want to rewrite equation A in terms of only u's and v's. We want to rewrite equation A only in terms of u's and v's. So, first step we do is, we put the definitions of sigma x, sigma y and tau xy from equation B into A. Once we put B into A, we will have A only in terms of strains, agreed. Once we put B into A, we get only equations involving strains. Then we put C into the new A. So, then those strain related equations become displacement based equations. So, it is fairly mechanical process. So, you can do it in your homes. That is one part of the thing we will not worry about in this course, but you please do this and convince yourself that whatever equations we are going to use further, they are correct. So, if I plug C and B into A, I get equations in U and V only. So, what are those equations? So, how many equations we will get? 2 equations. There were 2 equations of motion, we will still get 2 equations. So, the first equation is minus del over del x C11 ux plus C12 Vy minus del over del y C66 u y plus Vx is equal to Fx minus rho u dot dot. So, what does u dot dot mean? It is second derivative of u with respect to time. Similarly, from the second equilibrium equation, I get C66 uy plus Vx minus del over del y C12 ux plus C22 uy. So, please note that C12 is equal to C21. This is a property of our orthotropic materials. So, that is why we do not have C21 here. Here we do not have C21 because C12 and C21 are same. Okay. And this is equal to Fy minus rho V acceleration in y direction. And then we had relations for tractions, right. So, we will also rewrite relations for tractions as Tx is equal to C11 ux plus C12 Vy nx plus C66 uy plus Vx ny, and traction in the y direction equals C66 uy plus Vx nx plus C12 ux plus C22 Vy and y. So, these are equations of motion and these are for tractions. The second set of equations we will use later when we do the weak formulation. We have not yet started the weak formulation, but what we have done till so far is now that we have a displacement based formulation. Everything is in terms of displacement based variables u and v. So, that is what we have accomplished. So, let us call this equation A, let us call this equations B. Now, we will develop the weak form. Now, how many equations we have? We have 2 equations. So, to develop a weak form, what do? We multiply first by a weight function and then integrate it over the domain, and that integral is equated to 0, and then we reduce the differentiability requirement. Okay. So, now we have 2 equations. So, both these equations will be multiplied by 2 different weight functions W1 and W2. The first equation will be multiplied by weight function W1, the second equation will be multiplied by weight function W2. Then we will compute the residue, weighted residue, and then we will weaken the differentiability. So, So, once we multiply the first equation by W1, when we weaken the differentiability, we have seen again and again that when we integrate this thing whole thing over the domain and we weaken the differentiability, we also get a boundary term, okay, we get a boundary term. So, what I will do is, we know all this mathematics and we have done this several times. So, I will directly write the weak form. So, the weak form for the first equation is 0 equals He. So, the only thing is that we have developed the weak form and we have multiplied the weak form by a constant, which is the thickness of the element He. That is because later we will calculate some parameters, and if we multiply it by thickness, then they have physical significance. So, He is a constant, the entire equation we are multiplying it by. Okay. So, this is so this is first weak form. This is from the first equation. Similarly, from the second equation, so in the second equation we are going to multiply it by which weight function? W2. It is a different weight function. C22 Vy minus W2 Fy plus rho W2 second derivative of V in time integrated over the domain, and I am integrating it over domain, and actually, to be a little clearer, because I am in Cartesian frame of reference, then this d omega is nothing but dx, dy, dx and dy, and then I have a boundary term So, this is the second weak form. Okay. I am sorry, this is He and He. And we had said that it is a plane elasticity problem. So, the entire body is enclosed between two parallel planes, and the distance between those two parallel planes is He. So, the thickness of the body is He. Okay. Now, in this weak form, if the thickness of the body is extremely small, then you go for a plane stress assumption and you accordingly choose your C's. And if the thickness of the body is extremely large, then you go for a plane strain assumption and you again appropriately choose your C's, but the problem formulation does not change. So, these are the two equations. This is first equation, this is the second equation. Now, we look at this entire function. Okay. So, before we move further, we look at the boundary terms. We look at the boundary terms. In the first equation, the boundary term is W1. See, this is the boundary term. W1 times C11 Ux plus C12 Vy Nx plus C66 Uy plus Vx Ny, right. This is boundary integrand from first equation, which means that this tells me W1 is the variation in first primary variable, which is u. So, this means that u is a primary variable, and this entire term, what is this entire term? We have defined it earlier. This is traction Tx, agreed. So, this is Tx and this is a secondary variable. If I specify the primary variable, I am specifying the essential boundary conditions. If I specify the secondary variable, I am specifying the natural boundary conditions. Okay. So, this entire thing is Tx. Similarly, W2 appears in the second equation boundary term, which means the other primary variable is V. So, this is the other primary variable, and if I specify this variable, I am specifying essential boundary condition, and the other secondary variable is this thing. So, that is Ty, that is the other secondary variable. So, this is primary variable number 1, this is primary variable number 2, Tx is secondary variable number 1, Ty is secondary variable number 2, and if I specify it, I say that I am prescribing natural boundary conditions. So, with this understanding, we rewrite the two equations once again in the weak form. So, 0 equals minus He integral over the domain del W1 over del x C11 Ux plus C12 Vy plus del W1 over del y times C66 Uy plus Vx minus Wfx plus rho u dot dot integrated over the domain minus He boundary integral of Tx W1 ds. 2 मिनट बचा है, ठीक है. And the second equation is 0 equals minus He omega E del W 2 over del x C66 uy plus Vx plus del W 2 over del y C11 ux plus C12 Vy minus Wfy plus rho V double prime d omega minus He my Ty W2 ds. Okay. So, these are the two weak forms for plane elasticity problem, and depending on what type of C's we choose, we can either address a plane elasticity, a plane stress or a plane strain problem. Actually, first thing I have to say is that this negative sign will go away. What else? W this W1 yeah W1 W2 okay. Okay. So, this closes the discussion for today. Tomorrow we will develop element matrices for this problem, and then we will also learn how to assemble them, solve them, and also work out some specific details for this problem in next couple of lectures. So, that covers it for today. We look forward to seeing you tomorrow. Thank you very much.